VOAs and Higgs branches.
Yeah, thank you. So yeah, I'm Aiden, and in the second hour, I'll talk about a paper collaborator of mine put out recently on the archive. And so as I understand it, this first hour is meant to kind of be giving background that's necessary to understand that. And so I gave a similar talk earlier this year in Edinburgh, where I was kind of told, for the seminar, we want people to talk about associated varieties of vertex algebras, and can you do a talk on that? And so I started the talk and kind of briefly set up some notation for what vertex algebras were, and then moved on to associated varieties. And then everyone asked me, like, oh, what's a vertex algebra? And kind of what's some examples and things. So I had to hastily improvise a kind of introduction to vertex algebras. So this time I've prepared an introduction to vertex algebras and included the examples I want to use in the second hour. If at any point I'm saying too many things that people already know, let me know, and I can then switch to my notes from the old talk. But anyway, so I think for vertex algebras, it's one of these things that if you haven't worked with them, they seem like this really clunky and awkward type of object that are maybe a bit annoying to look at or talk about. And I'm hoping I can at least give some intuition as to what the use, like the usefulness for them is. So part one, what are VOAs? And so a question we can ask ourselves first is, well, what's a regular algebra? Which I imagine everyone in this room has multiple answers for this in their head already. But one approximate way we can think of this is, well, the answer is a vector space V with a map, which for vertex algebra purposes, I'm going to call Y, from V to NV, such that if I want to multiply two elements in my algebra, V, I just compute let's say Y of A and apply that to B. Now, of course, there's many types of algebras, and I could impose some other conditions on these things to ensure I have things like commutivity, for example, or having a unit or a derivation. But this is one way we can present kind of what the multiplication on an algebra is. So for a VOA, it's basically the same thing, except now I have some additional parameter. So actually, so I'll comment on this later, but there's sometimes in the literature a notational or a conventional difference between what people call a vertex algebra and a vertex operator algebra. For me, I hate this difference, so I'm going to use them interchangeably, but I will point out later on what the difference is. But let's just say for now, a vertex algebra is a vector space, typically infinite dimensional, but not necessarily, with a linear map. Which again we call Y, which goes from our vector space, but this time not into endomorphisms in V, but rather power series valued in endomorphisms on V. And so again, for the purposes of what I'm talking about today, you should imagine this is just a formal variable Z or Z. I've gotten really bad at switching between saying Z and Z in the same sentence. But however, in the context of physics and geometry, you should imagine this lives on something like, say, the Riemann sphere. And if you were thinking about like a generalization of vertex algebras introduced by Valence and Drinfeld, which they call chiral algebras, you could imagine this as living in some algebraic curve. And so some notation, if we have A in V, we would map that to A of Z. Where I'm introducing a notational convention where these AN are endomorphisms on V, and the nth one corresponds to the negative n minus 1th power of Z in the power series here. Other conventions are sometimes used, but usually when you see these parentheses on the lower index, it's using this convention here. And so, like with general algebras, we have some axioms we want to impose on this, but this is the underlying multiplication data. So what does it mean to multiply two elements? Well, if I have A, B, and V, then to multiply them, I do the same thing, except now I have integer many possible products I can use. So in particular, and just to be clear, if I wanted to write this in the same way, I could write because I'm taking the nth mode of this. Actually, and again, another notational thing, which is kind of annoying in the vertex algebra literature, these power series are usually called fields. However, in the context of physics, they're probably more accurately described as local operators in a 2D conformal field theory, or chiral local operators in a 2D conformal field theory. However, for the purpose of this talk, I'm just going to call them fields. But it's a bit of a misnomer. Okay, so it's the same thing. We just now have a family of products. Okay, so additional structure or axioms. And I think this is the bit where kind of vertex algebras are seen as very clunky because you see this long list of axioms and it looks a bit kind of confusing as to why they're there, but they're really not too bad actually. So one, we have a unit. There exists a distinguished vector, which is often denoted by the physics zero-ket notation and is often referred to as the vacuum vector, such that its vertex operator or the field associated to it is just the identity. Oops. Okay. And so in particular, along with some other axioms and things I'm going to sweep under the rug, because there's a lot of different equivalent ways I could define this. We want it to be such that if I take any arbitrary field and apply it to the vacuum, this is going to be equivalent to applying the negative 1th mode of that vector to the unit or the vacuum, which recovers the original vector itself. And this realizes the state field correspondence in conformal field theory. Okay, so the next piece of structure we have is a derivation. Okay, so we have a linear operator, usually denoted T for translation, because this corresponds to translations in physics. And it is such that what do I want to say? Its commutator with fields is the derivative of the field. I'll just write A of Z. Okay, so no, sorry, it doesn't follow from just this, but depending what order I introduce the axioms, I could go by and show that then we get this property. But I decided to just kind of say, with some other stuff, we want this to be true as well. So in general, I'll point out now, the fields in our vertex algebra. So there's kind of two ways you could think about these in a practical way. You can think of them in terms of the vector space and the vectors living there, and they have some like these multiplications between them. Or you can think of the operator algebra of the fields themselves. And in general, the axioms will ensure us that the multiplication of two of these fields will have finitely many poles. So we're dealing with Laurent series when applied to the vector spaces. So if I take any field in here and apply it here, I'm only going to have finitely many poles when acting on any state. But again, I think the definition can be messy, so I try to compactify things a little to focus on intuition. Okay, so now we're thinking, so we started off with saying, oh, it's like an algebra, but now we have a family of products. And now I'm saying we also wanted to have a unit and a derivation. And the final axiom that's used is essentially a pseudo-commutivity relation, which is also called the locality property. And this essentially says that for all fields in our vertex algebra, there exists some positive integer such that if I multiply the commutator of these fields, where the commutator is just the commutator on the endomorphism algebra, we want this to vanish if I multiply it by some sufficiently large power of z minus w. So the idea is you can think of, if I have a bunch of poles in this expression here, I'm kind of getting rid of those and getting something regular that I can make vanish. If it seems weird that I kind of have some non-zero things multiplying to zero, play around with the expression for the formal power series of the delta function and its derivatives, and you can see that you can get things like this appearing. Okay, I think that's the basic definition. Before I move on, did anyone have any questions about the definition? So I'll also state just in words that there's a super version of this. In fact, there's different super versions of this. The one which I'm going to talk about and refer to is that I take V to be a superspace, so Z2 graded. The axioms largely are unchanged. The derivation is still an even derivation, and the commutivity now takes this to be a supercommutator instead, is really the only difference there. And if I was being careful and talking about gradings, you would also want to check that gradings according to this sort of data have some compatibility with the super grading. And so, don't want to say that yet. And so one of the reasons vertex algebras are useful is you could ask yourself, well, why don't I just think of this as a very big Lie algebra? Because I can just take, and like I can think of all the data, all of these A's and B's as having commutators from the endomorphism algebra. So kind of what's some of the utility in packaging that data in this way? And I'll get more concrete with this in a moment, but the real utility, I think, comes from the fact that I can have a lot of these things. Like I can have infinitely many of these things in a bad way. So for example, I can have a Lie algebra that has infinitely many generators and relations, which breaks a lot of theorems and things. However, I have finitely many of these fields still. So it allows me to kind of deal with like these very big Lie type objects in a controlled way. And so the way that physicists and vertex algebra people make use of that is something called the operator product expansion. So there's kind of two ways I can take products between fields. The first is called the normally ordered product. So given two fields, A of Z, B of W, I can define something which is regular, has no poles in it. And I'm not going to write out the formula because I don't think it's very helpful to do that. But you should think of this as essentially as I take some big product of the ANs and the BMs, and then I take a similar other way round product, where if you're familiar with quantum field theory at all, the formula here is essentially going to say that I want my annihilation operators to the right. And this creates a well-defined non-commutative, non-associative product on fields. And moreover, it ensures that the locality axiom, it's closed under the locality axiom. So if I take a collection of fields which are pairwise local, all of their normally ordered products are also going to be pairwise local with everything else in that family. And so the other thing we want to use is the OPE, or operator product expansion. And so from the axioms of the vertex algebra, you can show that if I take two fields and look at their product, I'm going to get a sum over singular terms, which is given by this formula. And then I'm going to get regular terms, which are just given by the normally ordered product. And so this, again, the axioms, which I kind of swept how to see this under the rug, but we're going to have finitely many poles here. and we're going to have some infinite collection of regular terms here. And the reason that writing it this way is useful is it's only the singular part which is ultimately going to contain the information about the relations. One way to think about this is if I was actually doing physics and I wanted to compute correlation functions or something, I'd be taking a bunch of contour integrals or something, and it's just going to pick up the data around the poles.
Normally what the code always gives you a regular.
Yeah. I mean, proving that this is like I would have to write some formula here, and then you would have to do some work to prove it's regular. But it does follow from the axioms. Like it's not additional structure we're imposing on it. After here, like this is the axioms. Everything after this follows from the axioms. But again, the axioms have been slightly simplified just to keep it keep the data that's relevant more visible, I think. And so originally I was going to mention this later, but I'll bring it up now because I think this is kind of one of the things that I think is most useful. That if for example you have to work with vertex algebras and you like don't actually know how to do operations with them, this data is equivalent to the commutation relations of the mode algebra. So by mode algebra, I just mean the collection of every vector in all of its Fourier modes here. So in particular, I think this formula is quite useful. So in some of the examples I'll write shortly, these are essentially just going to be encoding the data of an infinite dimensional Lie algebra into these fields. And if you want to move between the commutation relations of the Lie algebra and the OPE, this is the formula you do so. So in practice, if you're presented a vertex algebra, it will usually be in terms of OPEs of some generating fields. And it will look like this with some finite number of poles. And just as another notational thing, since we kind of justify that the regular terms don't really contain interesting data for us, it's conventional to write a tilde here to indicate that that's just the singular terms. And so what you can do is you look at the numerators of each order pole, plug them into this formula here, and that tells you what the commutation modes are for each of the relations. And this is kind of how you move between these two viewpoints. And so yeah, in general, this thing might not be a true Lie algebra in that it might, again, require either infinitely many generators and infinitely many relations. But there are cases. So one example I like to think about, if you're familiar with this object, the W3 algebra, this thing, if you present it this way, requires like a lot of like infinitely many generators, but it's generated by, I think, just 2 or 3 fields for memory. Okay, so we'll go to examples now. Okay, so the first example, which I think is one of the most important, is the Virasoro algebra. So the Lie algebra, if you're not familiar, is generated by some LNs as well as a central element C. And the only non-trivial relation is that okay, so this is the Virasoro algebra, and it has a vacuum module, which I guess I'll call the C, which is induced from the trivial representation of the positive part. So I'm going to call the positive part, let's say, let's call it the plus equals ln for n greater than equal to -1. you might be wondering, why am I including -1 in the positive part? That's because there's a convention to write the modes not with the parenthesis notation I mentioned before, but with this other notation. So in the parenthesis notation, this is actually, I think, where the 0 is. But either way, we induce from this algebra the trivial representation, or the one-dimensional representation of this, whereby the central element C acts by some complex number little c, which is called the central charge. And this has this vector space, this representation, has the structure of a vertex operator algebra. So explicitly, we have the translation operator is given by L-1. The identity is just given by the unit of this guy here. And so I should mention now, I've said in words that we can think of VOAs as being generated by some collection of these fields. What do I mean by that? Well, I say some collections of fields generates the VOA, or strongly generates the VOA, if I can construct any other field as a linear combination of normally ordered products and derivatives of those fields. So kind of the operations I'm generating with respect to are normally ordered product, derivatives, and linear combinations. So in this case, the Virasoro algebra is generated by a single field. So we call it omega, and it's given by the -2 mode acting on the vacuum state. And so the vertex operator of omega, which is sometimes called L of z and sometimes called T of z, since this corresponds to a stress tensor in physics. But I prefer the L, I don't know why. And so you'll notice here that convention difference I mentioned, where typically for the Virasoro algebra, people don't use the parenthesis notation and instead have a -2 here. And the idea is that in conformal field theory, the weights of operators under L0 called conformal weights, and there's a convention where you would write the conformal weight of the field or the local operator here in this expansion. And so this generating field has OPE with itself. And so as an exercise, if you want to convince yourself that these data are the same, you can look at this OPE and plug it into this formula here and recover the regular Lie algebra relations. Yep.
Okay, the vector space is induced the algebra
Representation.
yes, that's representation. Again, the vector space is the vector space. Saying omega is L-2 applied to the back vector. What does that mean?
So, well, this guy this guy is an element of the Lie algebra,
Yeah.
acts on this thing of which this is an element. So it gives some other, yeah. So in general, you would write these things down in a PBW type basis where everything looks like N1, or like your monomials look like. So the elements of your vector space look like this. And in fact, for all the vertex algebras I'm going to talk about today, you would usually present like the vector elements looking like this.
And then if there's another piece of notation, you're saying L of Z is defined what happens or like why this omega.
Yeah. All right, so the reason I think whenever I see people give it like introductory talks to vertex algebras, they usually use the Heisenberg algebra as the first example. But I feel like the Virasoro algebra is more important because, and I'll write this maybe explicitly, but if a vertex algebra in general has a Virasoro vertex subalgebra satisfying a few compatibility conditions. So in particular, let's say I have in some other vertex algebra V such that in here, or in the endomorphisms of that, so I'll just say TV should correspond to the image of L negative 1 in here. And it should also be graded by the same operator as the Virasoro algebra. But essentially, when we have an embedding of the Virasoro vertex algebra into another vertex algebra, that's when we say it's a conformal vertex algebra. Or, again, this is the stupid notational thing, a vertex operator algebra. So for some reason, the convention is to add the word operator when you have a Virasoro subalgebra, which seems ridiculous to me because yeah, that makes no sense to me, but this is what people do. I and many other people use them interchangeably, but be aware of that if you read a paper and they say vertex algebra versus vertex operator algebra. Okay, so we'll do Heisenberg next. Yep. Oh, which board is this? Oh, okay. So just quickly, Heisenberg's generated by, let's call them ANs with classic commutation relation. Or you can in a canonical like coordinate free way find it as a central extension with respect to the residue pairing on Laurent polynomials. So what do I want to call it? Let's just call it H, little h. Depending what flavor you prefer. This also has a vacuum representation defined in very much the same way as here. And so I think this is also level 1, by the way. So let's write. And again, this has a VOA structure where I won't go into as much depth to save time, but the OP in this case is. And so I'm just going to make a comment. This is, again, not a technical definition, but a notational convention that I found confusing in the past reading papers, and I wish someone had maybe spelled out to me. But VOA people will often refer to some VOAs as being free field. And if you're looking at things from a physics perspective, these should be vertex algebras corresponding to free field theories in 2D CFT. However, if you're just dealing with vertex algebras, it's sometimes not clear which vertex algebras those are. One definition for what a free field VOA is ones where you only have a single pole in your OPE relations, and the numerator of that should only be a multiple of the identity field. So I shouldn't have anything other than some multiple of this appearing in the numerator. So in some mathematical sense, I could take this to be a much higher order pole, but as long as there's only one of them and I don't have anything interesting happening on the top, this could be referred to as a free field vertex algebra. And so I can generalize this story though, where if instead of just taking C here, oh, actually, do we prefer coordinate free or with coordinates? How explicit do we like things to be? Coordinate free? Okay, so the way I'd write this is if I replace this with, so let's have introduce a lattice. So I'm going to call it L integer lattice. Let's say it has rank R and it has a bilinear form. symmetric bilinear form. I can replace this part here with and then instead I now get a Heisenberg algebra associated to our lattice, which I might call HL. And this is essentially just going to be a bunch of copies of these guys, so I can introduce some new index here. I won't modify the right-hand side because all I'm going to do is write it on the OPE side where what did I call those? Phi. So this is a generalization of the Heisenberg to a higher rank, and I associate it to a lattice. And if you've heard about lattice vertex algebras, these are essentially extensions of these sorts of guys. Sorry? Yes, thank you. Yeah. And again, the definition's the same. I'm not going to modify the rest if everyone's happy with that. Okay, how am I I'm running low on time. Okay. Should I give the definition of the other vertex algebra I need, or should I talk about associated varieties and Jou algebras instead? I'll go into associated varieties. Okay, so okay, so I can define a filtration on any vertex algebra, which is called Lee's canonical filtration. And so this is defined as follows. So the pth part of the filtration is the span of, so I1 AI where the AIK is a finite set of strong generators of my vertex algebra, and we have the for each of these lower indices appearing here, we have NJ is positive and their sum is greater than or equal to P. So the way we can think about this approximately is that this is going to be the collection of things which have at least a pth derivative appearing somewhere. So if I unpacked all the things I wrote before about the derivation in particular, acts like a derivative, acting by derivative lowers the mode number of these things. And so this filtration is essentially breaking things down into how many derivatives were taken. Positive integers. As a vertex algebra. So if I had more time, I could write down the product and everything that shows you that it indeed respects the all these n multiplications I have. But yes, it's with respect to it's filtered as an algebra. And so in particular, yeah, I won't write that, but we will say you can take the associated graded with respect to this filtration. No, so this is something Lee had to prove in his paper. So he wrote this down. It looks like it might depend on this choice of generators, for example, but he was able to prove it doesn't, and it is canonical. Maybe not one that I'm aware of, though. But that would be nice, a cleaner way of writing things down. So yeah, the associated graded for this thing is just defined in the same way as it is for an associative algebra, I mean. And so again, in the talk, I'm Frankensteining with this stuff here. This has the structure of what's called a Poisson vertex algebra. Oh, maybe I should say. And so I'll say in words what a Poisson vertex algebra is. You can think of it as a commutative vertex algebra that has a collection of Poisson brackets. So kind of the interesting data is no longer in these regular mode things, but I now introduce some other operation on the positive nodes, which acts as a Poisson bracket on my vertex algebra. And so what we should think of these things is, given some variety, let's say X, I can look at its jet scheme or arc space. And so there's kind of this story where a Poisson vertex algebra is we want X to be Poisson. A Poisson vertex algebra is going to be the data of the functions on the arc space of a Poisson variety. And so the type of thing we want to think about is, well, can I kind of go from let's say functions, I'm just going to use this to mean functions. Can we quantize this in some way to get a vertex algebra? So maybe I should just write this arrow the other way and say, given a vertex algebra V, I can take its associated graded with respect to this filtration, and I'll get the functions on some Poisson, on the arc space of some Poisson variety. So that's one way I can go. However, is there a way I can go directly to the variety X? And the answer is yes, and this is the associated variety construction. So, sorry, it won't let me open my iPad because my finger's covered in chalk. Is there another board behind here? Yes. Okay, so if I take, there's this subspace, which for, I guess, historical reasons is called C2 of V, but for us, we can think of it as the first piece of that filtration. And so in particular, very explicitly, so this is essentially everything. This is going to contain everything that has at least one derivative appearing in the monomial expression in the vector space. And so we can take the quotient of V by this. And this has the structure of a commutative associative algebra, where the product is and moreover, this is a Poisson algebra with Poisson bracket. Given by the 0th mode. And so we can take the spectrum of this algebra, and the general idea is that this recovers this variety in this picture here. And so there's another thing we can do, which I won't write it. Sorry? No, not here. This is just kind of almost like not a coincidence, but this is some other construction that was later contextualized in terms of this filtration. But I was just using that to be like, oh, we've already written what F1 of V is over here, so I can just call it that here. But there's another, so this is called Jou's C2 algebra, or Jou's commutative algebra. And there's another much uglier construction for an associative algebra associated to the vertex algebra, which is usually denoted A of V. So let's just talk about algebras instead of spaces here. So up here we have R of V. It's a Poisson commutative Poisson algebra. And then here we had, let's call it P of V for the Poisson vertex algebra. And this other non-commutative Joux algebra, or Joux's associative algebra, which is denoted A of V usually, is a quantization of R of V. So in particular, I can take an associated graded of this and recover this guy. And so something we would like to do in general, but almost always can't rigorously at the moment, is I want to start off with well, in general, we would like these operations to commute, right? Like we'd like to be able to go around each way. And there are some cases where we can do that. Most notably the case of Drinfeld-Sokolov reduction W algebras and affine vertex algebras. In many cases, it's been proven you can move around here, but these theorems are level dependent. And there are cases where these operations fail. But outside of that, I don't think there's a general theorem proving these operations commute. And am I finishing at 10:02 or on the hour? On the hour. Okay, so I'll mention one more thing. So I'm getting like less and less technical as I go along. I don't know if that's an issue for people. So another thing to connect these things to geometry is, say I have, let's say, a cotangent vector space, and I perform some symplectic reduction with respect to some G symmetry. To go to some symplectic or variety X. And so we have a notion of chiral quantization. And so one of the vertex algebras I didn't write down, the beta gamma system, or also known as symplectic bosons or chiral differential operators. One reason to see why that name is the case is if I take its Joux's associative algebra, I recover the Weil algebra. But I can do a chiral quantization of this and get n copies of this chiral differential operators. And so there's a question of, well, can I do the same over here and come up with a vertex algebra whose associated variety is X? Sorry? Yes, thank you. I think actually in a version of the paper I wrote, I had dimension of big N equals big N, which wasn't great. But yeah, so the question is there some VOA such that the associated variety, which we usually call X sub V, which is spec or max spec, depending on if you care about the scheme structure or not. So the question is, this would be called a chiral quantization if I can produce some vertex algebra whose associated variety is the thing I started with. And I could combine this sort of diagram with this here. And you might be asking, well, what's the operation that goes from here to here? And this is called BRST cohomology or BRST reduction. And with respect to some G symmetry. And in general, this diagram does not commute. Again, in the case of if I were to put, but there are a few cases where this sort of diagram does commute, but really not many in general. Yeah, so one should think of chiral differential operators as somehow being associated to like the cotangent, fiber or structure of a space, with the beta corresponding to the base point coordinates and gamma, for example, corresponding to the fiber coordinates. In general, X isn't going to be a space that supports that type of structure. However, there's kind of, I guess, this intuition, which is when we're dealing with varieties which are symplectic and symplectic reductions, can we construct a vertex algebra that does this? It may use something other than these beta gammas, for example. Like, I think that's somewhat of an open question of, are there things other than beta gamma I can use to quantize? I don't know the answer to it. Oh, I know some things about this, but I don't think there's a good definitive answer for this sort of thing. So was there any questions?
But like, are you saying that too many cotangent bundle like a nice DF canonically, or is it?
No,
like it goes-
so in this example I was drawing, this was just a vector space. Like not necessarily like a bundle or anything. In general, I can't construct a sheaf of these things. So this is kind of like the global object. Yeah, sorry, I'm terrible at getting it's much more natural to sorry, the arrows weren't in the ideal situation there. Anyway, this is the sort of thing which is going on in the setup I'll be talking about shortly. Since I haven't had time to spell out a lot of details here, is there anything kind of like burning questions about any of these objects?
What's about instead of the form like positive state, that's about benefits back to veristic homology. But I mean, first of all, veristic homology you can only take if you're lucky, right?
Yeah.
The level has to be like twice critical. And
So
usually that will not be the case.
So yeah, in general, the thing people want to do is take a space, construct a sheaf of CDOs, take global sections of that, identify it with the RST cohomology for the global sections, identify that with a vertex algebra. There's a lot of obstructions or points where what I just said can go wrong, but there are a number of ways of adapting this story to get something similar to what you might want. There's a theorem which says that a sheaf of CDOs exists on a variety or can exist on a variety only if the second churn characteristic of that variety vanishes, which for most spaces we care about doing this to isn't true. So cases where that is true is like algebraic curves and flag varieties. But more generally, we have to do something. And so this obstruction corresponds to a gauging anomaly corresponding to this gauge group. And so physicists, what they do is they throw in some odd variables. And so instead of just looking at chiral differential operators, we also look at chiral differential forms. So maybe I should just write down the relation just very quickly for those two algebras because they're important. So chiral differential operators. It's going to be something like delta ij. Is that right? Do I have a square there? Yep, no, there is a square. And so these are even, but then I also have an odd analog of these called the BC system. And so when I take the collection of these things, which, I might call beta gamma, this is called, or if I take a sheaf of these on a space, I call these chiral Durham complex. And this always exists on a Poisson variety. So the physics way typically of resolving this anomaly is to, instead of taking the global sections of a sheaf of chiral differential operators, is to instead take the chiral Durham complex. And the things that add to that are odd. So in many cases, we only care about the variety structure, not the scheme structure. And so things don't change too much. There's another construction which you can use to resolve this too. So there's a paper, I forget the title, but the author I think is pronounced Chabatarov from about 2011. And he constructs something which he calls deformed twisted chiral differential operators. And so this is a purely even sheaf of even vertex algebras I can construct on any space I could construct the chiral Durham complex of. And this will give a different thing. So in what I'm going to talk about, there's another paper which does the story we're doing. However, instead of using the chiral Durham complex, he used deformed twisted chiral differential operators and got a different associated variety in the end. So there are different things you can do to get around this sort of obstruction, but they're giving you kind of like there's some choice you have to make about what are you actually interested in studying. Like it's not just I want to chiral quantize this, what do I do? And I'll make one more comment, because yeah, this is my last minute. I mentioned there was an obstruction to a sheaf of CDOs existing. There's a little more than that even in general. if your sheaf of CDOs does exist, it might not be unique in some way. In general, you're going to get a gerb of these things, and there's some freedom as to what's going to happen. And that's characterized by the first like cohomology, or like the first characteristic class of the variety instead of the second one. So in general, if you do want like a unique, well-defined sheaf of CDOs on a variety, you need kind of you need to have things quite constrained. Yeah, no, I'll stop it there. If there's any questions, let me know before the next talk. Do we now take a 10-minute break, or? Okay.
Take this chiral complex and you look at the associated variety, you get back Poisson homology.
Sorry.
Like the chiral complex, when you take like the semi-classical or like the associated graded.
Sorry, which are you talking about, RV or AV?
Okay, so it sounds like this is some complex on a space
Mm-hmm.
associated to this vertex algebra. So like when I take the associated graded, like there's this functor.
This thing?
Yeah, yeah.
The
there's a
Poisson
functor-
vertex algebra.
There's a functor from vertex outpost to Poisson variety or Poisson schemes. And this, when I
Just on jet schemes, you should.
sure,
like-
sure. Or I guess there's like this functor as well. So if I start like this one, it goes to here, right?
Okay.
Which gives me
So just to clarify, this is an infinite dimensional thing. This
Yeah.
is a finite dimensional thing.
Yes.
Yeah.
So this thing going here, is like, what happens to this when you follow that arrow?
So,
Does it recover an invariant
well,
of the Poisson variety? Like some.
sorry, are you asking about the finite dimensional thing?
Yeah, yeah.
Yeah. So, I mean, I think this is just going like, and you want the commutative thing.
Yeah, yeah.
So it's just going to give functions on the space. I'm not sure what the odd guys tell you exactly.
Okay.
But like doing it with just beta gamma when I can do that, that's just going to be like functions on like some cotangent space or something like that.
Okay. So it's not like, is this like a literal like chain complex though? Can I think of this as like a chain complex? Like it's a Durham complex?
Yeah, I think complex like these like derived things of VOAs are kind of weird because in some sense a lot of the time they're like have some natural grading, but it's all concentrated in degree 0. So yeah, so it's like kind of weird. Like it's almost always going to be derived in a dumb way. Then there's the question of, and this is actually something I've been thinking about a bit about recently, is there like another like set of derived data hiding somewhere? I don't know a good answer in general to that. Like again, like if I get this, can I get a chain complex back out?
Yeah.
I would say I don't, to my knowledge off the top of my head, there's not a natural way of doing that.
Because I'm just thinking very silly, like you have a way of taking VOAs to Poisson things.
Mhm.
So chiral will go to a Poisson thing. So then there's like a Poisson Durham complex.
Yeah.
As well, where you can deform the differential on forms using the Poisson tensor. So I'm wondering if like when you take this functor into Poisson,
So I
recover this.
I will say if we look at these two guys, this inherits a grading from this.
Yeah.
Like the quantization of that. In general, I think this is kind of the grading that should be like the correct derived thing. I don't know what happens to the differential or like how you can reconstruct the differential from that. One thing I had been thinking about recently unsuccessfully, or when I say thinking about as in like in the past few months, that it's like instead of starting with just like a like algebra of functions on some space, is like start off derived and go, hey, I have a DG commutative algebra. Is there some way I can now take the construction of CDOs or chiral Durham complex on that space where the thing I associate to it somehow remembers the differential from that DG algebra on that open subset, and then encode that in the VOA? That's the thing which is confusing me though, because again, I feel like if I gave you an example, or if you gave me an example or something, and you were like held a gun to my head and was like, oh, you need to give me the differential for this thing, I could probably artificially put it in, like guessing based on like the grading I'm getting from this sort of thing. But yeah, I don't know in general. So for example, the Higgs branch thing I'm going to talk about, that should be a derived like symplectic thing in general.
Let's go get coffee.
Yeah. I should probably take this off. Well, I don't know if someone's going to be listening. Oh, back in. Probably eat 2 out of today. I was like, wow, well, like not semi-simple, like long CFT categories are useful for like a real world application. Yeah.
And if we really want to be serious about it, we can have like a gong.
That would be nice.
You could set up like a fire alarm or something.
Well, that would be pretty counterproductive.
So the new fire alarm convention is to congregate in this room. That's not a fire.
Yeah, I think the administration might not like that.
Of course, I have to leave a little.
I won't be offended.
If they want to do.
I'll take all the most incorrect
I
things
just
for the
want to
last.
tell you that you love me, but I don't like what you're saying.
So if you leave 20 minutes early, that is because you're like. We're starting right now.
Yep.
Oh, okay.
There's a mic.
Wait, where'd I put my iPad? Okay, so I'm going to stop talking about vertex algebras briefly and just give a general context to the paper I'm going to talk about. So this was joint work with Andrea Ferrari. I don't like this piece of chalk. And so the general context of this is 3D mirror symmetry. So I think a bunch of you already know the general gist of 3D mirror symmetry, but I'll go over it anyway. So the kind of thing we want to start with is a 3D quantum field theory with n equals 4 supersymmetry. And in the wait, sorry, show of hands, who knows what a topological twist is already? Okay, I'll still briefly explain what a topological twist is. So in the symmetry algebra for the space-time of such a theory, there exists two operators, QA and QB, that both square to 0. So Q squared equals QB equals 0, and these are called supercharges. And roughly speaking, I can look at the structure of my quantum field theory through the cohomology of these square 0 operators. So I start off with some theory T, and I can pass the cohomology of either QA or QB. And it turns out that the translation operators are exact in this cohomology in each case. And so what we get are two topological field theories, TA and TB. And these are sometimes referred to as the 3DA model and 3DB model, or the A twist and the B twist. And so a kind of approximate fact about these is that the algebra of local operators of TA, for example, roughly corresponds to the functions on a hyperkähler manifold known as the Coulomb branch. And similarly, if I put TB here, I get a different hyperkähler, functions on a different hyperkähler manifold called the Higgs branch. And so what these are branches of is the moduli space of vacua for the full theory T. So if I look at all the vacuum expectation values in my theory T, it forms some manifold. And these have two distinguished branches called the Coulomb branch, which comes from the gauge fields, and the Higgs branch, which comes from scalar fields. And so what 3D mirror symmetry posits or conjectures is the existence of a mirror theory of a theory of the same type. And by same type, I mean 3D QFT with n equals 4 supersymmetry. Sorry, you're saying 3D mirror symmetry, like by saying 3D mirror symmetry, like this thing already exists?
they just take the same field, so there's define something. It's just because some automorphism of the superpower, right?
Oh, right. You're saying like when I do the thing that takes this to that, and yeah, okay. Well, the thing I wanted to write was that as like fully extended TQFTs, we would have something where the A twist of one is the B twist of the other, and vice versa. This isn't fully well defined, I believe, because I don't think the fully extended structure has been well defined. So in particular, what this functor assigns to like, I think the three-dimensional object is like involves one of those integral problems that comes up in physics and isn't well defined. But like in principle, this is the sort of thing that 3D mirror symmetry says should be true.
Yes, but modulo is technical. This statement is
Okay. Modulo existence of these things, this should be obvious if you actually write down what the symmetry algebra is and all these things. But the reason I wanted to write this was saying if we combine this kind of statement with this statement, you arrive at kind of the main thing people talk about with this, which is that the Coulomb branch of one theory should be isomorphic to the Higgs branch of the mirror theory and vice versa. And so when people talk about the study of 3D mirror symmetry, like I feel like 90% of the time they're talking about this type of correspondence and data associated to it. And so sometimes this is also referred to as symplectic duality. Though I believe there's examples of symplectic duality that don't arise from 3D mirror symmetry, and there's aspects of 3D mirror symmetry which don't derive from symplectic duality. So I think they are technically distinct. I mean, I thought this was a half physics seminar. I should be allowed to talk about things that don't exist.
I think that's about whether one falls from the other. It's kind of difficult to say because.
Yeah, I think maybe symplectic duality is in principle better defined.
No, because there's no statement.
Well, there's no general statement about what class of like the most general class of symplectic resolutions this duality applies to. But in some magical completed version of this world where all the information is thrown in, morally, I think something like that should be true. Okay, where was I? Okay, so I could write some examples of this. So I mentioned before symplectic resolutions. So it isn't really just a duality between like manifolds. It's also between let's say resolutions of singular symplectic varieties or hyperkähler in principle. So you start PN. So these are resolutions I'm writing. So things like the Kleinian singularity, flag variety, where we get the Lagrange dual. Hypertoric varieties, which is what I'll be talking about. And the dual is given by the Gale dual, if you're familiar with this. So we have a algebraic symplectic reduction of a cotangent space by a torus. Here we take kind of a dual torus instead, and then take algebraic symplectic reduction with respect to that. And more generally, like ADE quiver varieties, Nakajima quiver varieties, and affine Grassmannian slices. So a lot of cool spaces appear in this sort of story. Okay, now I know you're all missing me talking about vertex algebras, so we're going to go back to vertex algebras. And so one way we can study this is using a boundary vertex operator algebra construction introduced by Costello and Gaiotto in about 2018, I think. But I think I've been told that some version of this existed in Davide's work before that, but I'm not sure as many people read that. And so the idea is, if I look at the twisted theory with some certain holomorphic boundary condition, and I look at the bulk here, so I can think of this as 3D bulk, 2D holomorphic boundary condition. And the idea is I have local operators in the bulk, and I can look at what happens to these on the boundary. And then these are going to behave meromorphically and support the structure of a vertex algebra. But there's a bit more than that. And I should note, sorry, this is when I say local operators, I mean in the topological twist. So there's a version of this for both the A side and the B side, but I'm going to be thinking primarily today on the A side. And so I also have line operators on some one-dimensional subspace X. And there's this usual story where if I have like a defect at my boundary, this is going to be a module for the algebra here. So I can think of the local operators on the boundary as acting on the intersection of a line operator on the boundary, and this gives it the structure. So I have a vertex algebra, which I'm going to call V, A, or B. And then so line operators are going to give modules for this boundary vertex algebra. And in particular, if I took this to be the trivial defect, so the defect where it changes nothing, then that's just going to recover a local operator here, and it's part of the algebra itself. And so this kind of picture leads to the first conjecture, which was, I think, stated first in Costello, Kreutzig, and Gallardo, which is the category of line operators of the twisted theory is equivalent to some derived category of boundary vertex algebra modules. And so the thing is, these line operators should have some braiding and tensor structure. And so the tricky thing, I think one of the trickiest things on the vertex algebra side of things is identifying what this module category should be. So for example, we know what this module category looks like in the abelian case, but outside of that, I don't think we have a good idea of even like an SL2 case or something. As vertex algebra modules? We know what this is, but we don't. Yeah, okay.
Whether you can write it as modules of some algebra, that's sometimes you're not supposed to. So lucky you can, but you don't.
So I mean, just a slight digression here, but in this paper, they write a section which is like a proof of the I think the H twist they call it, which is the A side. And they essentially talk about you take D modules on the loop space of the Higgs branch, and then they identify those with chiral differential operators on the Higgs branch. But I think there's a bunch of, at least to my knowledge, there's a bunch of technical kind of things which need like to make that a theorem. And well, because I was looking at the first or second year of my PhD, I was looking at trying to fill in those gaps, and I quickly found that was really hard. Sorry, are those technical issues? Like the identification of D modules on the loop space with CDOs on some space seems like a difficult thing to prove, maybe outside of some simple examples. But for vertex algebra peoples, this category is hard to define. So the idea is we have some definition for a boundary vertex algebra, and we would like to construct a braided vertex tensor category that lines up with the expectations for how the line operators behave. And we have a good rigorous definition for what this is in the abelian case. But yeah, so if I then combine this sort of picture about line operators being modules for the boundary vertex algebra, and it's a fact that I can recover local operators in my theory by taking endomorphisms of the trivial line defect. Well, the trivial line defect corresponds to the vertex algebra itself, or the vacuum module. And so the next conjecture, which was also due to CCG, is the the derived endomorphism algebra in this category should reproduce the functions on the Coulomb or Higgs branch. And so again, this has been proven in the abelian case, but outside of that, I don't. Sorry.
If you can see the right category, so I mean, let's get with it. Cover the 3D proposal. Yeah, and so.
It's a vacuum.
It's the algebra itself is a module over
Yeah,
itself.
so that first of all, they have a category associated. Yeah, this is this guy.
Yeah, but what is the element of the category? Yeah, okay.
And so if it takes the morphisms to get the spaces to sphere.
Yes.
So it's an algebra, so that's what the functions from the things of Coulomb branch are.
Great.
That's and then somehow the whole question is whether you can write this category as module of the sum for this algebra. That's great.
Yeah, what he said. Unit object. And so there's another story as a brief interlude, where in fact, I'll just say this in words. In 4D physics, for a theory with n equals 2 supersymmetry, or superconformal field theory, I should say, there's another construction of vertex algebras where essentially I take a certain class of operators called show operators, and I pass those through to the cohomology of a supercharge in the superalgebra plus an operator in the conformal part of the symmetry algebra. And if I pass to the cohomology of this guy, I get another vertex algebra, which is characteristic of the theory. And so if I then do a compactification from, well, at least in some cases, I can do a compactification from 4D down to 3D in such a way that the Higgs branch of the 4D theory is the same as the Higgs branch of the 3D theory. And so this point of view led to another conjecture, which I think was first explicitly written in Beam Ferrari, though I think it kind of appears in this paper less explicitly, which essentially says that the associated variety of the boundary VOA. Actually, sorry, this is particular to the A side. The boundary, the associated variety of the boundary VOA should be the Higgs branch of the theory. And so this is the conjecture we prove in at least one case for our paper. Okay. Any questions on this general setup? You mean on this side? Yeah, you have like a CP1 of these things from the hyperkähler structure. Is there like a distinguished one, are you saying? I don't know. Do you know? Oh, do you know? What is it? What's the like distinguished Poisson structure on the Higgs branch?
This is I mean, when I say Higgs branch, what do you mean?
Like, am I taking it as a hyperkähler space or a?
Definition of type K.
Fine, Poisson variety. Define Poisson generically subjective variety. That's the only mathematically great definition.
Right.
And so then maybe it has sometimes it has revolution, sometimes it doesn't, and so on. And so but on the node, I mean, for example, for gauge theories, you can explicitly define as some kind of methodic reduction.
Yeah, so in fact, that's the next thing I was going to write.
But the point is the Poisson structure is complex.
Yeah, everything is complex. I mean,
Yeah.
everything is so complex.
Yeah, so it doesn't come.
Okay, so, oh, sorry, was there any other questions? What do you mean by de Rham algebra, sorry? This? Yeah. I mean, to me, so are you saying like what's the definition for Higgs or Coulomb branch generally, or
This one.
this?
Yeah.
Like what type of algebra is this? I'm not familiar with the de Rham algebra, so I can't say if it looks like it or not. I don't know, sorry. Okay, so I'm now going to only be talking about the A twist with gauge group G and cotangent matter representation. Oh wow, time flies. Cotangent matter representation, where I'm going to say again the dimension of big N is little n.
Vector space.
Yes, this is a vector space. And then so for such theories, our Higgs branch, most generally we would want to take as the reduction of that representation by the gauge group. And so, as I mentioned before, naively, the thing we would want to call the A-twist boundary vertex operator algebra would be the global sections of chiral differential operators on here. But as I mentioned previously, that doesn't always exist, and in most cases we care about it doesn't. And so we modify and use the chiral Durham complex instead. And so in particular,
This thing sometimes, it's cheap.
yeah, so this should be like a DG stack most generally. No. So I was going to say, I was talking about this recently, and the question of can this VOA construction see the DG and like stacky structure of this sort of thing? And I think there's remnants of it you can see from the grading inherited by the.
Where does that DG start? Is N
So really this should be like a derived symplectic reduction.
Ah, yeah, okay. Great.
So they global functions of the I mean, you want to do something affine, so you want the functions of the potentials that are more G, but it's still potentially G.
Yeah. I think in general it should, like, you should be thinking of it as DG, but I think in practice most of the papers in this sort of story.
It's shoe algebra, can upgrade it or something.
This I was literally talking to Aiden about this in the break, and so I've talked to Davide about this a little bit before, and I mean he's repeatedly said something about how there should be like a DG version of vertex algebras that like retain that structure. Yeah, but the thing is, like the vertex algebra I'm about to define is already kind of a DG object concentrated in degree 0, and so like the natural like grading structures and things that come with aren't really the ones we're interested in. I think, I don't know, like I haven't proven, but I think that I had this quantization, sorry, like the non-commutative Jou algebra going to the one giving the associated variety. I think the grading that this inherits would at least be the grading that you would want to come from this. I don't know about like differentials or anything else, or where that data might be hidden somewhere. I suspect a better construction is needed. Sorry, I'm going. Well, actually, I'll say one more thing that I don't. Surya and Brian and Nick, have you seen their Raviolo vertex algebra papers at all? So they essentially use like a holomorphic topological like factorization algebra, put it in coordinates so its axioms look like a vertex algebra. And they in one of their papers end of last year, I think, they showed you can get like the Higgs and Coulomb branch from some simple examples out of that, and that does come with the DG structure. So the answer to the question might be, instead of using vertex algebras, maybe you should just be using like something that's keeping more data, like the holomorphic topological factorization algebra, or something like that. It would be nice though if there was like a way to translate that into VOA language, which then kind of makes connections with more other, you know, topics and things. Anyway, sorry, that's a bit of a tangent. Okay, so yeah, naively what we want to, well, not naively, I'm just going to jump ahead and say the definition of our boundary vertex algebra is going to be the 0th BRST cohomology of our beta gamma BC system. And in fact, this is you can think of this as a relative semi-infinite cohomology if you're familiar with that language. And it should also be noted, at least in the abelian case, you can prove that the BRST cohomology vanishes in other degrees. But so I could just put like the full thing here if I wanted.
It knows the range is such a great level is correct.
So sorry, what do you mean by level in this situation? Like,
I mean, you don't take your ST reduction like the bubbles twice.
so
That's kind of the reason why you want this permanence. Because you want to take a PC system, the level won't be correct. But I don't think you can always correct it by permanence.
I think the statement's something like there always is a level where you can correct it. Sorry, are you talking about like?
It's a perfect algebra which contains the smoothing of some specific level.
Yes. Yes.
Then we can just use the level is not correct in the sense that we cannot take the reduction. And then you want to answer it with some kind of cleaver algebra. So that the reason you want to take it.
Yeah, I mean, I know in coordinates when you write this down and you get the current in terms of this and you kind of balance it with a current from this. Mm-hmm.
Can figure out on the spot, can you always arrange it in such a way that the level is.
So saying, can I choose any level?
Have a freedom here, namely freedom for which PC system you're multiplying. So the question is, can you always arrange it in such a way that you are allowed to take your reduction?
So sorry, in just to be explicit, are you
This is a response to some representation.
like it's going to be the number that appears on the numerator in the OPE, right? Because this is then going to change what the multiple of the. So in our case, I can tell you if we put 1 here, it works and we get the right thing. I don't know if I change this to something else if it stops working. I can chat to you about it later if I catch you later. Anyway, okay, sorry. Let me just figure out where we should go with this. Okay, so I'll just review briefly. So a large part of this story in the abelian case was figured out in a big paper, a 160-page paper by Borland, Kreutzig, De Mofta, and Noy. And so they look at the case where G equals some torus, and one of the results they do, well, I'll say a few things. They prove that you indeed recover the Coulomb branch algebra from the derived endomorphisms of the boundary vertex algebra, and they show that they define what the correct module category is, and so in particular, roughly speaking, they look at beta gamma modules which are induced from Weyl algebra representations, and then take some completion with respect to certain extensions. And so importantly, though, they give a general expression for what the BRST cohomology for the A side VOA looks like. And so roughly speaking, this is going to look something like okay, so rho is a matrix which encodes the action of the gauge group on the representation and is unimodular. H is an abelian group which results from decomposing the charge lattice with respect to the one given by rho. Sorry, this should be Z. And by the mirror charge lattice. So if you're familiar with Gale duality, these are kind of like Gale dual charge lattices. And so this gives some abelian group. And this expression here, these M's are some big direct sum of tensor products of let's call them M tildes, where these are irreducible representations of the triplet algebra or the W3 algebra at central charge -2, I think. And these are Fock representations of a certain generalized Heisenberg algebra. And these are also just direct sums of Fock representations of a different Heisenberg algebra. And this part here essentially corresponds to stuff coming from the fermions, and this is stuff coming from the bosons. And what we'll note is that if I look at the zero, if I take the identity guy of this, I get something which I could call, let's say, M rho 0 tensor M rho 0. And this forms a vertex algebra, which in the case of our paper, which I'm probably not going to have much time to talk about, but if I take R equals 1, so a U1 gauge theory or superquantum electrodynamics with n hypermultiplets, we showed that the bottom level of this decomposition was isomorphic to the simple quotient of SLN at level -1, and then this last guy here corresponded to level +1 SLN. And so when you see an expression like this in like VOA literature, where you have a direct sum over some abelian group, where all the higher guys are simple modules, or in the tensor category, invertible objects in the module category for the bottom guy, this is called a simple current extension. So essentially, they gave some general expression of the boundary vertex algebra in terms of free field realizations and simple current extensions. We were able to unpack that and identify that it was in our case, it was a simple current extension of 2 copies of SLN, one at -1 and one at level 1. And another result due to Adamovich, Kreutzig, Yang, and others shows that the level 1 PSL n/n VOA is a simple current extension of this thing here. And so with the matching, we're able to identify the boundary vertex algebra as this PSL n/n guy. And just a quick note, I said level 1 PSL n/n. I feel like this is a slight misnomer. One reason is that there's kind of, well, not a misnomer, but there's a level duality here. So negative K and K give isomorphic algebras. But moreover, I think there's only 2 cases of Lie superalgebras which actually have 2 central extensions. So I could in principle do a second central extension and have a second level here. I've spoken to all the people who prove these results in their papers and asked them, oh, like, what's the definition of your normalization for your level? And I brought up the fact that there was a second central extension, and no one seems to know the answer. So I think there's some ambiguity in the literature about which central extension corresponds to the level here, but I think the one we've picked is the conventional one that everyone else has been using. But I just wanted to highlight that to, what's the word? Public service. Okay, so that's kind of like the first half of the Higgs branch conjecture proven for SQED at least. We've identified the boundary vertex algebra. For the second part, we then need to show that the associated variety of this is the Higgs branch. And so the Higgs branch of this theory is the closure of the minimal nilpotent orbit for SLN.
I think it's a specific presentation or start with your G is torus, right?
Yeah. So I gave kind of this general expression for a torus. Yeah, and now I'm taking R equals to 1. N is any n except depending on which part of the paper you read, n is either greater than 3 or greater than 2. So oh yeah, so this is the representation defined by the charge matrix, like where rho is just
any focus of the standard.
Yeah. We actually did play around with a few different ones, but it's not that interesting. At least, like, we can't identify things with nice looking things, so we didn't worry about the other guys too much. But yeah, so we want to now show that the associated variety of this thing is the minimal nilpotent orbit closure. And the unfortunate thing is that there's not really a whole lot of literature on the representation theory of like affine PSL and n/n. But one thing we do know is that, well, we know this is a simple current extension, and there's this subalgebra in here of even things. And we do know a lot about the representation theory and associated varieties of these things. Sorry, which?
SL M count.
n/n,
SN/n.
like the same n. And so results due to Arakawa and Amuro. Tell us that, well, I'll just write, no, I'll write it properly. So for the negative level 1 guy, we get the closure of something called a sheet of SLN. I'll explain what this is in a moment. And for the other guy, we just get a point. And this is kind of, I guess, nice to see, because as I said, this level 1 guy came from this kind of part of the decomposition. And this is the part coming from the fermions. And so in some kind of way, adding in the fermions has kind of changed things not too badly. It has changed things, but it hasn't changed things in kind of a drastic way. Whereas I meant this.
Yeah.
So this is like bold face S I'm using.
Oh, okay.
So like in the same way the minimal nilpotent orbit's like O bold, this is like S bold.
And what is that?
Okay, yeah, so I'll say that. So in the same way you can kind of define minimal nilpotent orbits in terms of the sizes of their Jordan blocks and requiring them to have 0 eigenvalue, we can define sheets in a similar way where we're saying everything has the same sizes of Jordan blocks. However, we're now allowing non-zero eigenvalues. So one general definition for a sheet is if I define M, oops, hold on. Let me write this correctly. Yeah, so if I take M to be the set of X in my Lie algebra such that the dimension of the centralizers of those elements is M, the sheets are the irreducible components of these things. And if you do a bunch of work, you can show that these sheets, again, this is kind of type dependent, and I've only thought about these in type A, so take everything I say outside of type A with a grain of salt. You get that the sheets all contain a unique contain a unique nilpotent orbit. And so we can kind of classify the sheets by partitions in the same way we can Yes. Yeah, so it's like a Levi decomposition of a parabolic. And then, so in particular for the guy we care about, I can write this explicitly as some central element here, and then the nil radical of some parabolic subalgebra whose type is determined by the type giving the minimal nilpotent orbit. So in particular, if these guys have like partition this, then the Levi subalgebra corresponding to this nil radical is going to have a conjugate partition type, so like n-1, 1. And so this thing is codimension 1 in here, and the difference between them is some semi-simple element. And so essentially, what we did is we go, okay, we're using kind of the structure of the Jou algebra. We're able to argue that the associated variety for this guy has to live inside the associated variety for this guy, which is the sheet. And then so what we want to do is show, okay, well, it's not actually this guy. It's going to be some codimension 1 subvariety of that. And we want to get rid of the elements corresponding to semi-simple matrices inside SLN. And so the way you would usually do that is go, well, we know what, so I didn't write this in my pre-talk, but this guy is the simple quotient of some universal affine VOA. And so the idea is, if we knew what the maximal submodule of this is, we could just like look at the images of elements in that maximal submodule and see what functions they give us on the associated variety and hope we get ones which correspond to semi-simple things. However, we don't know what the maximal submodule of this is. And so in general, the maximal submodules of these affine VOAs are going to be generated by what are called singular vectors. So if I have a decomposition of my affine Lie algebra, triangular decomposition, then a singular vector is essentially a weight vector that is annihilated by the upper triangular part or lower triangular, depending on your convention. And a sub-singular vector, which you may have to worry about, is something that's singular in the quotient of a module generated by a singular vector. But anyway, so things in PSL n/n look like this, where we have an SLN here, an SLN here, and then we have some odd things. And so we know what the submodule structure of these two guys is. And what we want to now find is a bigger module that contains both of those, plus some new stuff that we hope gets rid of the semi-simple guy. And so if I use EIJ to denote the elementary supermatrix corresponding to this, then we were able to find a new singular vector coming from the odd part, which was given by this formula. And so we then proved that the module generated by this guy contains the maximal submodules of the SLN subalgebras. And then we were able to also further show, well, okay, let me step back for a second. So the Zhu C2 algebra is going to delete anything with lower modes than this. So we kind of only care about things which are constructed out of these -1 modes. And so the image of those is going to correspond to functions on SLN dual, which we can just obviously, for this case, identify with SLN. And so the defining or a defining ideal for the minimal nilpotent orbit closure is the functions which are the 2x2 minors of the matrices. Now, which of those functions are not in the defining ideal for the sheet? Well, it's going to be the 2x2 minors with elements lying on the diagonal, the semi-simple guys. And so what we were then able to show was that, well, if we look at the image of this, the submodule generated by this under the Zhu C2 functor, we were able to show that we get the remaining 2x2 minor functions which have entries lying on the diagonal. And so what this lets us conclude, but we're not quite done yet, but what it lets us conclude is that our PSL n at least lives inside the minimal nilpotent orbit now. And so to complete the proof, we now need to argue that it's not something less than that. But luckily, that was quite easy to do. And so the way to see that is, in general, the associated variety for a quotient of an affine vertex algebra should be a G invariant variety. Moreover, we know that the associated variety of a vertex algebra is going to be a point if and only if that vertex algebra is C2 cofinite. So in other words, this subspace is cofinite. So when we take the quotient by this, we get like a trivial, like the associated variety is just going to be a point if this guy is cofinite. And as a result, or maybe more of a comment by Katz and Soganova, which tells us that this Lie superalgebra vertex algebra is not on the list of things which have a possibility of being C2 cofinite. And so we can rule that out as being C2 cofinite, so we know it's not a point. So we know then, like, this doesn't equal a point. But we know it has to be some G invariant variety. So in particular, we have an action of 2 SLNs acting on our associated variety, with this one coming from the non-trivial -1 block. This guy's just acting on a point. But this is an orbit, and the only thing inside it is the trivial orbit, which we know it's not. And so we know then it's the minimal nilpotent orbit. Okay, I have 5 minutes. So that's kind of the rough proof of the Higgs branch conjecture for SQED1. We've been working on a few extensions of this idea, including deformations, other levels, and things like this. Still work in progress, but we're finding some interesting things relating to rationality and cofiniteness conditions. So in particular, I mentioned this C2 cofiniteness condition, which is like an important condition in vertex algebra literature. The Higgs branch kind of tells you about this because the associated variety's size. So for example, if it has finitely many symplectic leaves, it's kind of quasi C2 cofinite or quasi Lie. And if it's trivial, well, then it is C2 cofinite. So the Higgs branch tells you about how finite our vertex algebra is, or how well behaved it is in that sense. The Coulomb branch, on the other hand, tells us something about extensions of the vacuum module. And this relates to the notion of rationality for vertex algebras. So This essentially is the condition that a vertex algebra has a semi-simple module category. And so what we're kind of hoping to understand is that there's kind of an old conjecture for VOAs that this is now a false statement, that C2 cofiniteness was equivalent to rationality. I think like in the 90s, people believed this. There was a counterexample to this, which was the triplet algebra, which was shown to be C2 cofinite, but not rational. It's still an open conjecture, I believe, whether the other implication is true. And I think the belief is it's probably, well, yeah, okay, I changed my mind about whether I believe it or not. But what we were hoping to do is to use the Higgs branch and Coulomb branch of a vertex algebra to understand what's the kind of precise relationship between these two conditions, because this is very much a Coulomb thing, this is very much a Higgs thing. Sorry. We don't know. We've been trying to. It could be. So the one method we were trying to come up with is like we're looking at examples where we know we have a point on one side but not the other. And unfortunately, those examples haven't really provided us with any new information so far. You're saying like trivial resolution.
Well, I mean, resolution is not that's supposed to be smooth and only keep branching.
I'm not sure. Is that a theorem? Sorry, you're studying? Okay. I suspect if that theorem is true, it would tie into this story. But at least from my point of view, I'm not aware of such a connection yet. We were hoping to find such a connection from the examples we looked at, but so just to see why this kind of story falls apart a little bit, there's a relationship between so if I look at my derived endomorphism algebra, the reason this thing isn't like immediately trivial, like so if I'm in the associative algebra world, like this is going to be trivial immediately because like an associative algebra is going to be projective over itself. So the idea is if we want to look at this module category being semi-simple or not, is there an associative algebra way to tell that? Well, we have the Joux algebra construction. And so we can think about this. And with some kind of technical assumptions added, the Joux algebra should be able to tell when your category is semi-simple. So like that's not an if and only if statement. I'm forgetting off the top of my head which way it goes. But this thing in some sense should be able to detect when we're semi-simple. But this guy is always going to map to something like this, which is always going to be projective over itself and is always going to vanish. So there's some missing piece of data to unravel the connection between these things. And that's something we're working on by looking at deformations of this story, where the deformations take a non-semi-simple, interesting module category and collapses it into something semi-simple. So when we did a deformed BRST reduction of this story, we're able to show, in fact, earlier this week, I think I wrote the proof for this, is that you do get a semi-simple module category in those cases. Stayed longer than he said he would. But yeah, no, so we're still trying to understand kind of the connection between these two conditions and how the Higgs and Coulomb branch can tell us about those. I can keep ranting, but I think that's actually my time. Yeah, I'll stop there for your sake.